Okay, let's continue with interrupts. So we talked about hardware interrupts, and we'll review the hardware interrupt concept first before going to software. Now, so there is a concept called interrupt vector, sometimes called interrupt vector table. So interrupt vector is a table of addresses. What kind of addresses? Well, addresses to interrupt service routines. So that means when you have interrupts coming in, each one is associated with an index. And so with a table, think of it as an array. You can index an array, right? And this, you can think of it as an array of function pointers, so to speak. But these are simpler than functions, because function is more of a C programming language concept. In assembly, you have what's called subroutines. A subroutine is a piece of code you can kind of jump to and then be able to return to where you jump from. Okay, and so it's not so much a jump. It's actually more of a go to and then with a return. And where's the return address? Well, it's pushed on the stack. So now with an interrupt vector, basically you think of it as an array of addresses. And if you have a like serial port, you have a keypad, you have timer, whichever, each one has a number associated with it. And so that number is used as index into this table, namely interrupt vector. And so the hardware knows how to do the index operation, fetches the address from that table, and that's where it goes to. Okay. Now, on 8051 works slightly differently, but I mean that's really the key concept. But we'll just use this concept. Basically, think of it as the array of addresses. Even though on 8051 it's really little where you actually could place the interrupt service routine. What oftentimes happens is the first thing you do is jump out of it and then goes to this other place to handle. Anyway, so there's a service routine associated with for device I, and that's what it does. So the user program can run along, and then interrupt comes. Hardware makes the call to service routine sub I, and then when it finishes, returns to user program. User program doesn't know it got interrupted. Now, what about software interrupt? So software interrupt could happen when you do an explicit trap instruction. On MIPS, trap is called Syscall. There may be different names for it, so that's one way. That means if you want to request a system service, you make a system call. And oftentimes the term for it is a trap instruction. And well, what kind of service? Well, it's encoded in an integer. So you do a system call with a service ID. Okay, so 0 could be for like halt, 1 could be for output, 3 could be input, 4 could, I'm just making this up. But in C.H file, you can see all the system call numbers. Now, in addition to a trap instruction or explicit request, you could also have errors. Like divide by 0 could cause a trap, or it could cause a, sometimes people call fault. So page fault is an example where you think there is memory, but it hasn't been allocated. So when you try to do a load or store to a memory region that's invalid, then causes the fault to happen. And again, that's a kind of software interrupt. So there is an entry in there that corresponds to handling of page faults or handling of divide by 0 exception type of thing, right? So there are different ways for software to cause interrupt-like behavior, because by interrupt-like that means the program goes along, it never does the jump, but then the hardware forces a jump to the corresponding handling routine. Okay, so what's in common is CPU suspends execution of the current program, transfer controls to the handling routine or interrupt service routine ISR. And where does it figure out where to go? Well, by looking up the interrupt vector, which is an array of pointers to functions, right? Or pointers to routines, so based on the associated code for it. And then as part of doing that, it has to save the address of the user program where it got interrupted so that it knows where to restore to. Okay? And now, when you're running an interrupt service routine, guess what? Another interrupt could happen. So that's called nested interrupt. All right? And why is that? Well, you could have devices of different priority levels. Perhaps one is handling serial port, another one is handling this interrupt or reset or some other event. It may be higher priority. So while handling one interrupt, another could come in. So what does the processor have to do? Well, exactly the same thing that has to do to interrupting a user program. It then has to remember which interrupt got interrupted and then saves the state. Then it jumps to this higher priority one and then finishes doing that. So that lower priority interrupt service routine doesn't know it got interrupted. Okay, and it has to keep doing it until the highest level interrupt possible. Okay, but what happens if you have a higher level interrupt that's being serviced? A lower interrupt comes in. Sorry, it got blocked or got masked. Okay, so that means it might have something and it couldn't come in. Well, what does it have to do? It just has to wait. Okay, and but how long can a device wait? Well, it depends on the device, and some may have limited time. And so when the processor finishes servicing a higher priority interrupt, can the lower priority interrupt still be there? Well, it could, but it could also go away. And in that case, you lose that interrupt. Okay, how could it go away? Well, several things. It could be that buffer overflows, or it may have to be responsive. And if it's too long, then yeah, it's meaningless. And so there's many different possible ways this could be handled. But anyway, just so that you know, then we'll get a chance to do some interrupt coding as well. Okay, so now, so far we talked about system organization. This should be mostly review for you guys. Bootstrapping concept, interrupt versus polling. So you could do polling, and that's probably the first thing you would try when working with a device, because you just want it to work. And once polling works, you probably want to convert to interrupt, because that's a more efficient way. And you should know the steps in handling an interrupt, what the processor does versus what the routine does. Concept of trap, which means software-initiated interrupt-like behavior, right? Handled same way as what a hardware interrupt does, except there's no external event. It's all part of executing instructions, whether it's a trap instruction or some faults. Okay, next we'll go into a little bit of storage hierarchy. And so as you know, memory down to storage can be viewed this way. So closer to the processor, the faster, more volatile, more expensive, right? So registers are part of the processor, part of the instruction set architecture. You have only a handful of these, by less than a K. Caches, larger than registers, most likely. A little slower than registers, and in fact, quite transparent to the instruction set. And you can have multi-level caches. Right? You should know this from your computer architecture class. And main memory, and cache has a faster copy of what's in the main memory. And these are what's called volatile memory. Why? Because if you power off, content is gone, right? And next time you power back on, you lose everything. But there's non-volatile memory, so solid-state disk, flash memory card, USB stick, hard drive, optical disk, down to magnetic tape. These are non-volatile because after you power off, the content stays around. You can still get it. Okay, you don't need battery to remember the content. But then they are much slower to access. Why? Because they're optimized for bulk storage. That means a lot of bits per dollar or per monetary unit. And their speed tends to be much slower compared to the higher level memory hierarchy. Tape used to be the cheapest, but nowadays you don't use tape as much because disks, well, maybe not so much optical, but even magnetic disks has gotten so high density and so cheap now. Okay, so for storage device hierarchy, right? So they are ranked by size, speed, cost, volatility, right? Main memory is still part of a concept related to the processor, even though it's outside the processor. Why? Because the processor has to have the notion of the address space, has to know how big and how to address memory. So the memory structure has to work with the interface defined by the processor. Now you can have SRAM or DRAM, and SRAM is faster, higher power, more expensive. DRAM is what you most likely use. It's much lower cost per bit, and that's what it's in most systems. But for embedded system, you're likely to have SRAM. Now, secondary storage is more non-volatile, so your flash memory, SSD, magnetic disk, and so forth. And caching, that's a kind of an add-on concept to processors, especially for RISC processors. They really take advantage of caches so that you can get faster access to memory. Otherwise, the memory latency is really long. And so it's a copy of what's in main memory. And so when the processor tries to fetch something, it goes to cache first, maybe simultaneously goes to memory. But if it's a cache, it doesn't really try to access memory. So it takes a local copy, and it's assumed to be the freshest. And in case of cache miss, oh, it's not in memory. Then it goes off to main memory, and you pay a penalty. But by probability, you pay a lot less penalty overall, because most of the time you expect it to be a cache hit. That's due to principle of locality. There's two kinds of locality: temporal locality versus spatial locality. These are just review, right? You should know this from your computer architecture class. And the caches have different size and replacement policies. Okay, now concept I brought up a little earlier and related to memory is direct memory access, or DMA. So this is where the device controller is transferring a block of data. Think of it like, if you read from your disk, you don't read a byte at a time, even though, yes, you could write your call to be one byte at a time. When you go down to system call, it gives you a block at a time, buffers it, and your call fetches from your buffer 1 byte at a time. Okay, so the transfer is done in bulk. And do you want the processor to do a byte at a time or a word at a time? Not likely. That's not very efficient. Usually it's done with a DMA. Same thing with your Wi-Fi, with your other bulk transfer. It's done one block at a time, one packet at a time. And that way, basically, you set up a shared memory structure so the device controller, as hardware, on the bus can read or write a region of memory on its own. It's shared with the processor. Processor can also read and write memory, the same one. But how does it work? Well, yes, of course, the memory controller has to figure out if you have conflict. And you may have to support multi-ported memory. And if you try to access the same one, or there's some arbitration required. But fortunately with caches, the processor doesn't have to go to memory as much, because most likely it's a cache hit, right? So it just accesses the cache without having to go to memory. So that way there's no contention. The DMA can happen, just keeps dumping its data from to memory or fetching it from memory. Processor can put everything up in memory, and then it just does it on its own, right? And it can overlap. That's great. And then upon completion, the controller that handles DMA sends a notification in the form of interrupt to the processor, and the processor, oh, okay, done. Yeah, great. I'm just gonna move on to the next thing. Okay, so it generates one interrupt for every block transfer, usually half a K, 1K, or how many K. Okay, oh, half a K is common, and then it handles it one chunk at a time, as opposed to one word or one byte at a time. Okay, so DMA works like this. So the processor is running and sends an I/O request to device or through device controller, and so here device really means it talks to device controller, which then talks to the device itself, and then there's some data transferred to device, but then really what is more efficient is the DMA way. The device directly talks to the memory and then sends an interrupt back to the processor. Okay, so that way it's much more efficient. The CPU doesn't get involved on the fine-grained level. Now, there's two kinds of memory I talked about, and these should be reviewed from your architecture class too. So SRAM versus DRAM, you should know the difference. SRAM, for static RAM, uses on average 6 transistors per bit. Sometimes you can get it down to 5. And it's easier to interface because it's static, and fast access retains its content as long as it's powered. And so caches use SRAM. And some embedded processors have SRAM on the same chip, and they're much smaller compared to general purpose ones. Now DRAM is when you have like hundreds of megabytes, gigabytes, tens of gigabytes. DRAM is more practical, uses one bit or one transistor per bit, and they're also manufactured differently, and they can be done more in the vertical dimension to pack a lot more density, much lower cost. But when you access, you have to do what's called row and column access. And in fact, they even contain small SRAM buffer to help this. And also, these single bits are leaky. So every so often, what has to happen? Refresh has to happen. What does refresh mean? That means some controller has to read out one unit at a time into SRAM, writes it back, right? And then otherwise, the bit will leak away. It's a transistor, it's a leaky bucket. And so it needs refresh, otherwise it loses data. And that's why its structure is more complicated, and it needs additional controller. But these are all pretty well understood. And the access takes more time. So if you had to deal with that interface, yeah, it's kind of a pain, but oftentimes hardware people already take care of this for you. Okay, lower level disk mechanism, you have disks. Some of you already switched to SSD, so you probably don't worry about disks much. But these are still in data centers. Every time you do like a cloud access, most likely they still have a disk farm somewhere. And so a disk, you should still have seen something like this, right? It's a box, and inside there's probably several platters. So you might think, oh, a disk, one. No, it's actually several stacked together. And then for each one, they can do most likely the rewrite head above and below that each platter. And so the disk spins, and then what happens is then it has these tracks. Track is a concentric ring. It's a circle, and then you have inner tracks, outer tracks, and then and each track is divided into sectors. Okay, and then of course there's the track could spin either at constant rate or variable rate, because on the outside you can travel more distance, and supposedly you can store more data, right, compared to the inner tracks. And so you're supposed to have more sectors on the outside than on the inside for the same track. Anyway, so what the disk has to do is two parts. One is there's the spinning part, so you have to rotate, and depending on disk, you may have like 5,400 RPM, 7,200 RPM, or over 10,000 RPM. That's rotations per minute. And then there is the ARM assembly. What does it have to do? It moves to different tracks. So the inside or outside of the disk, right? So the inner part, where it's a smaller radius, or outer part, the larger radius. So there's rotation latency and what's called seek. The seek is that movement from the inner track or to outer track. So it has to position itself to the right track and then wait for the disk to spin around to the sector that you need. Then it can start doing the reading and writing, okay? And so that's what a disk does. So there's two latencies, the seek time, which is the arm in and out, and rotation latency, which is the platter spinning to the right place, okay? And so as you can imagine, these drives, magnetic disks, are kind of slow because it's a physical device compared to a solid-state disk, which is just essentially flash memory packaged up with control and for wear leveling, for other things, and some combination with caches, buffers, SRAM to make it faster access. So I'm not going to test you on the actual speed of these because these technologies keep evolving over time. But people are predicting your SSDs are going to take over magnetic disks at some point. Maybe true, but magnetic disks have shown amazing ability to keep increasing in capacity without much increase in the cost. And there's just a lot of innovations there. But still, a lot of these disk companies are still hedging their bet and are also putting out these solid-state disk products at the same time too. Anyway, so with caches, you have potentially some coherency issue or consistency issue. Well, it's not so much an issue unless you're dealing with shared memory, okay? So if all you have is processor, cache, main memory, what could happen? Well, the only part is like your DMA could write to part of memory. And you try to work on the cache, oh, sorry, the memory's been updated by DMA controller, so your cache copy is out of date, right? So because a cache is supposed to be a faster copy, but the assumption is your processor has the latest copy. But if somebody else makes the update, then your cache copy could be out of date. That's a coherency issue, okay? So DMA could cause cache incoherency in even a uniprocessor. But oftentimes, the processor knows what it's doing. It knows that part is for DMA. Unless it's a naive program, otherwise it should know. It shouldn't really be an issue for uniprocessor. But nowadays, you have shared memory processor, multi-core. These are multiprocessors that share memory. Each one may have its own cache. Could be level 1, level 2. Maybe level 3 is shared among multiple cores, but some level might not be shared. What happens? Well, if they share memory in their communication, one processor says, I'm going to change this shared memory location. The other one, well, what should happen? If you don't do anything, then it's going to access the stale copy or outdated copy in its own cache. So in multiprocessors, what should happen is if it's shared memory, then you should do what's called cache invalidation. Because you change the copy and you have to tell all the other shared memory processors that that location is no longer updated, mark it as invalid. So then next time that processor tries to access that location, what does it do? It gets a cache miss, right? Because that location got marked as invalid, has no choice but then goes to the free memory, goes to main memory, get the latest copy. Okay, that's what a multiprocessor has to do in order to avoid a cache incoherence issue. Okay, so and that's done through invalidation. All right, so quick review. We talked about storage devices, caching, DMA structure, and how DMA works in the cache architecture. Is actually cache helps not only with performance but also it reduces contention with DMA. Different memory types, SRAM, DRAM, disks, and cache coherency. So a lot of this is supposed to be a quick review of architecture. Okay, let's talk about hardware protection. Dual mode operation, we talked about it in the previous hour. This is really for hardware to provide the right kind of support so that OS can do its job, protecting and managing resources, protecting access, right? So one is really that how does OS ensure a program, whether intentionally or unintentionally, cannot corrupt another program's resources, including data, I/O, and all that. So that means if you want to access a resource, you better make a request to OS. OS gets control and decides what to do, right? And so to do that, you want to have at least 2 levels of privilege. User should run in user mode, and then OS should run in what's called monitor mode, sometimes called kernel mode, sometimes called system mode, or privilege mode. These are all synonyms, okay? Monitor mode, kernel mode, system mode, privilege mode. And we'll use these terms interchangeably. I mean, it shouldn't be too difficult for you to figure out. All right, so dual mode operation. Well, not all processors do this. 8051 doesn't have dual mode operation, but that shouldn't stop us from doing an OS-like kind of service. And because I think this is actually relatively easy because it's really not work done by OS, it's work done by the processor, right? The processor just has to have a bit that is set either by instruction explicitly or by part of side effect of executing an instruction. So how do you switch between user mode and kernel mode? Well, from user mode to kernel mode, several things you can do. One is an interrupt comes in. Yeah, so the interrupt service routine runs in kernel mode. So as part of handling an interrupt, processor not only interrupts or suspends a current user program, it actually does a mode switch to kernel mode and then runs the interrupt service routine, okay? And trap, well, software interrupt, but same idea. If you issue a system call instruction, if you do a divide by 0, if you have a page fault, if you have access violation, that's a software interrupt, same thing, goes through kernel mode and runs interrupt service routine. And the interrupt service routine, you can imagine, is part of what the kernel functionality, kernel has control over it. And so you can say, once it's in interrupt service routine, the OS can get access or can get control. And then it can decide when to return back to the user, okay? So now privileged instructions, on the other hand, are these instructions that are allowed only if you are running in kernel mode. So if in user mode you try to execute one of these instructions, well, sorry, the system or the CPU will disallow it. And what happens? Well, it causes another software interrupt. So OS gets control anyway, okay, if you try to do a privileged instruction while in user mode. And so now, so what are privileged instructions? So if you do direct I/O, try to read-write your serial port, try to set a timer, try to access other functions, right? Move your page boundary. These are things that are supposed to be all privileged, right? So, or even return from interrupt should be a privileged instruction. Okay, here let's look at a concrete example. MIPS is a RISC architecture, you probably know, right? So derived from the Stanford MIPS architecture, later turned into a commercial product, and a lot of textbooks use the MIPS instruction. So it does have one instruction called Syscall, and it's a way for user code to request OS to do a service, to do a system call. Kind of obvious, a syscall. And how does it request? Well, you have to just tell the OS which service to request, right? So that means there is a corresponding number, the service number. What does it do? Well, it has to load into register V0 as part of an argument you pass. So RISC architectures like to pass arguments not on the stack but in registers. Okay, no problem. So it loads up V0 register with a call number, and then maybe additional, depending on the call, you may have additional arguments. Fine, the A0, A1, A2, these are for arguments, right? And so, then it does a syscall. Then what happens? Well, it generates an interrupt-like behavior. So it doesn't actually do a subroutine call. Basically, the interrupt mechanism kicks in, and because there is an interrupt number index associated with syscall, Then the CPU looks at this, looks at interrupt vector, that index in there. That's the handler or interrupt service routine for Syscall. Goes there, and then there's a case statement, and then goes and looks at which number it is, then does the corresponding thing. Okay, that's what a system call does. So, and then it does a return from interrupt, and then the call continues. So Syscall itself, is it a privileged instruction? No, it's not, right? Because that's the whole point of Syscall, from user mode to request a system service. If it's a system, if it's a privileged instruction, then you can't make that call, right? So it's a user instruction, but its effect is to make a system call, right? And part of the effect is to transition into system mode or kernel mode, and then system can service the request or deny its request. Now, once it's in system call in kernel mode, to return from it, in MIPS instruction set, you have to use ERET for return from kernel mode. Then that is a privileged instruction, because it then switches back from privileged mode back to user mode, right? Well, where it came from. Now, in addition to this kind of system call instructions, I/O instructions need to be privileged. To offer the protection, the I/O devices can be shared, and you don't want different processes to be able to make the I/O directly. You want them to go through the OS to make the request, and OS can then serialize them or decide access. So a lot of times, for example, even your mobile device, right? Sometimes, like, you're doing something that requires microphone or speaker or camera, right? These are I/O devices too, and you don't want any program to be able to access these I/O devices anytime. You want the OS to take care of this. Either the OS can say, only one app can use this camera at a time or microphone at a time. Or maybe it has a way to route these to multiple apps. I don't know. It's maybe a decision the OS has to make. Now, what about output? So speaker, do you only allow one app to output to the speaker or merge? Well, I've seen the cases where it actually allows multiple apps to do this at the same time, right? So one is playing music, the other is talking, and so it actually may have a way to figure out how to resolve these potential conflicting requests, right? It may not be conflict, it may have a way to resolve them. So OS can make these decisions, but still, the overall idea is you want to make requests through the OS instead of letting the programs access these devices directly. And so that's why these have to be done through system call, and in fact, the actual I/O has to be done in privileged instructions. And another thing is, these service routines are defined in the interrupt vector, right? That's just a table. That's just an array. That part of memory had better be protected too. Why? Because imagine, that's an array. I can define array at this location too, right? Who's to tell me I couldn't reference address 0? And if I can specify any pointer, I can read, I can write. Let me replace that interrupt service routine with my function, right? And so when the user hits a key, jumps to my function as interrupt service routine. Suddenly I'm a user in kernel mode, right? Isn't that great? Well, yeah, so that means you shouldn't allow the interrupt vector to be modifiable by user program. That part has to be protected too. So protecting I/O is not just about using privileged instructions. It's about protecting the associated memory locations as well. All right. So how do you protect memory? I mean, that's another software limitation. Software can do all it wants, but user code ultimately can find a way to touch memory it's not supposed to touch. That's why you really need hardware to help you do the protection, in addition to switching mode. Okay? So how does hardware provide memory protection? Well, a most straightforward way will be what's called base limit registers. So base is the starting address, and then limit is how many bytes down. So you basically allow each process to access memory only within this region, okay? Because simultaneously, you can have multiple processes loaded into memory at the same time. So here, you guys see, I'm showing monitor, which is the OS, job 1, job 2, job 3, job 4. Suppose job 2 is executing, and one way to do memory protection is you have a start address, which is the base address, right? Address 300040, and presumably in hex. And then limit is how many bytes. So then what you do is then, that means the end address is 300040 plus 120900. And that gives you 420940. That's the end address. So any address that's within the range between 300040 and 420940, that's allowed, access normally. But if the job 2 is trying to dereference or access memory outside, then hardware will disallow it, gives control back to the OS, right, through another software-like interrupt. Okay, so the flowchart goes like this: base plus limit. The CPU does 2 checks: the address, and if it's greater than equal to address, okay, go on to see if it's less than base plus limit. Yes, then actually lets you access memory, and hardware can do this very quickly. You don't even have to write instructions to do this. Hardware just flows through, and you can pipeline this easily. Now, if either one is a no, traps to OS, right? The corresponding service routine gets called. Now, what about other types of protection? So CPU protection is another one. And what that means is you want to prevent user from hogging the CPU. I mean, not physically. I mean, they can hammer on it. There's nothing you can do. But protecting CPU here means protecting its CPU resource, which is the cycles, right? What could happen? You could write a program in infinite loop that happens. I mean, I didn't mean to. Just had a bug, and I didn't check this. It's an infinite loop, and you don't want a bug to slow down everybody else and prevent others from making progress. And right, so it could be intentional or unintentional. That shouldn't bring down your system. And because I mean, if all you're doing is relying on interrupts and system calls, what if my program never makes a system call or doesn't hit any keys? Then that means OS never gets control, right? That wouldn't be so good. So what can you do? So then that's where timer comes in. So pretty much all CPUs come with some kind of timer, and it regularly, or it can be configured to regularly generate an interrupt, even if the user doesn't make a system call or doesn't do anything. It just does its own infinite loop, right? And so what does a timer do? It's basically a counter, and you know counter from your digital logic design class. You count number of cycles, and there are several ways to do it. You can either count up or you can count down. A count up when usually like upon rollover, so from FFFF to all zeros, that's when it can generate one interrupt, right? Because that's a carry bit out, simple. Or some can do countdown timer, so decrement until it hits 0, that's when it generates one. Doesn't really matter. And this is commonly used for time sharing, okay? Which also means any changes to the timer should be a privileged instruction. If not, the user can just keep setting the timer and then they never time out and never interrupt, which is not good, right? So the access to timer should be a privileged instruction because the OS relies on it to take control back on a regular basis so that it can decide how to, whether to keep running the same one or give somebody else's a chance to run. So timer interrupt, so it works just like any other interrupt except it's internally generated by its timer hardware. So timer, and 8051 certainly has timers. It actually has 2 timers. Timer 0, timer 1. We'll use timer 0 for the purpose of causing these regular interrupts so you can do preemption. timer 1 is used for the UART, the serial port. Anyway, so in this case, we just assume when counter reaches 0, it could be a rollover or something, it generates an interrupt, and it looks just like any other external interrupt. Okay, so OS defines the ISR for the timer, and so when the timer interrupt comes, the user code could be generating all they want, and then OS gets control back through the interrupt service routine for the timer. And then what it can do is from there, it can run a scheduler, decide what to do, context switch to another process, or maybe it can do some bookkeeping and say, hey, this program has been running for too long. I'm going to lower its priority, or I'm going to kill it, or whatever. Right? So now that's what an OS can do. But at least OS has to get the control back. Okay, okay, so dual mode operation is something that the processor supports so that OS can run in the privileged mode, whereas user program runs in the less privileged mode. It restricts its access to resources, which only OS can do. And OS can request the user code can request OS to do things through system call, right? And that's through Syscall or trap instructions or other interrupts. And then OS gets control through the execution of these interrupt service routines, because interrupt service routines run in privileged mode and are defined by the OS. And the OS certainly also need additional protection from hardware for memory access. Otherwise, users can still try to gain access by changing, say, the interrupt service routine address, right? That way, because it elevates interrupt privilege level to kernel mode, and if they can change the interrupt service routine address, then jumps to their code, they run in privilege mode, which is not good. Okay? So memory protection is also an integral part of what the hardware has to support, and that's something that OS can't just do it by itself. It really needs the hardware to do the enforcement. And CPU use is protected by use of timer interrupts, which can interrupt user code even if they don't make any requests. It forces them to surrender control. OS can decide what to do and give other processes a chance to execute. Okay, so that is the quick overview of Chapter 1, and I'm going to continue with EdSim from last time. And this week, Wednesday, I have additional material to cover. So here, I just wanted to maybe backtrack a little bit. So we talked a little bit about these instruction. You should definitely go and take a look at the data sheet for 8051. And so move instructions, there's these combinations allowed, right? So you can move to the accumulator, or move to a register. So this is destination. So you can think of it as destination gets source. That's how you should interpret these move. Yeah. So A is a accumulator. It's not a register in the sense of R0 through R7. So R0 through R7 are registers in the sense. Yes, the term register has been overloaded, but in this context, register here is R0 through R7. Okay, and in fact, more specifically, the at reg, that's limited to R0 and R1. At least 8051 does it. You can't use at R2 or at R3. So reg, so yeah, interpret this to be R0, R1, R2 through R7. And then at, that means take the register content as the pointer and dereference it. Okay, so that's how you can use like a pointer, and you get to write code here in this course to do this. And now dir is for direct address. So remember, you have IRAM is a single byte. So from 0 to 128, 127 actually, and so that's where you can see on a sim display. And now source is more, right? You have register or add register. So R0 to R7 or at R0 at R1. Pound sign immediate, right? You know what an immediate is, right? That's a constant value. So if it's 17, then now you have to do pound sign 17. Otherwise, if you don't have pound sign, just have 17, that's location 17 in IRAM. And in this format, you can A immediate direct or A immediate direct register or add register. Okay, so you can have other combinations. We talked about this last time, right? So you can't move from one R1 to R2 or another register to another register. That's not allowed. Only the combinations here are allowed. See here, reg or add reg. Here they don't allow another reg. So when you write code, if it complains, you need to know why, because certain combinations might not be allowed. And move A to A doesn't make sense. And move pound sign 20 comma R3. You can't assign. In C you can do 20 gets X. Doesn't make sense, right? Okay, now ports are P0, P1, P2, P3. So they correspond to direct addresses 80, 90, A0, B0, but all hex. Okay, and so so you can do move to P1 or you could do move to 90 hex. As direct address. Either one is okay. You can do the symbolic name or address name. It's okay. Now, these are also bit addressable. So you see the names. P1, you can do P1.0, P1.1, P1.2, and so forth. So you can do 8 bits at a time or 1 bit at a time. So if you do 8 bit at a time, you can do move and then P1 as the destination. P1 gets like hex 5EH. So hex 5E. Right? And then 5E is interpreted as big endian bit order. So 5 is the higher bit. So 0101, that's 7654, and then 1110 for E, that's bit 3210. Okay. Another way is you can do bit addressing. So instead of move, you can do set bit or clear bit. So set bit means assign bit 1. That's what set means, at least in 8051. So P1.1 gets 1. That's what set B P1.1 means. CLR clear, and that's P2.3. So that means set the port to bit 3 to 0. That's what it means, right? So you can do either 1 byte at a time or 1 bit at a time. But you don't use move when you use bit access. Now, 7-segment LED. So each one has 7 segments. You can address them individually. And actually, next set of slides on Wednesday will show you the exact mapping. There was probably some issues with the previous one, but some of you tried it and figured out. Anyway, so these are tied to P1. So if you set the zeros and ones, you could cause these LEDs to light up, but only one at a time. So how does it work? Well, there is this decoder here. The decoder takes 2 bits from P3.3 and P3.4 and decodes so that it's 1 bit at a time. And this is the power supply side, right? So you see Q0, Q1, Q2, Q3. One of them will be enabled, and then that becomes a power supply into one of these bits. So by setting the bits P3, P4, you control power, which power to send to one of these LEDs. So what does that mean? That means you are actually only turning on 1 digit at a time. And so in order to show all 4 digits at a time, what do you have to do? You have to keep setting P3.4 and P3.3 to 1 value at a time. Those 00, 01, 10, 11. You keep cycling them. And then at the same time, you set them to different values. Because the processor is supposed to be run really fast, by cycling through them quickly enough, your eyes can tell the difference. Okay, so that's how they intend for these 4-digit LED to be used. So So in the simulator, it might not refresh so quickly, but on the real 8051, yes, it'll be really fast. Okay, so you should be able to fake it. So in order to display like 2019, you have to select digit 3, display the 2, the segments for 2. To select digit 2, you then set the bits, the P3.3, P3.4, and then display the 0, and select digit 1, and then the digit 1, and select digit 0, and then display the segments for that digit, right, for the 9, and repeat. So that's how they intend for these 4 to be used at the same time. But you can do this, right? So, I mean, given that, you should be able to interpret this code. All you have to know is sjump here. So what does this do? Well, there's a label here called top. A label is just the target location. It's a symbolic name for that location. And so set B, so that means set bits 3.3, 3.4 to both 1s. And then move, remember this move to P1 of #24? That sets that digit, remember from last time? And then now you clear one of the bits in the P3.3, and then you move this one. So that means you select a different 7-segment LED and then set its segments, right, to the 2, 4. And clear another bit, set another bit. So this is to cycle through these digits, but all displaying the same digit, right? Same digit value. So we could try this, and once you get this to work, you know what it does, then you can make the modification. See if you can print out 2019 by yourself, okay? And what it's gonna do is just show one digit and then goes away, next one, next one, next one. But if it's running for real, it's gonna be really fast that you can tell that it's flashing. But on the simulator, you can tell it's flashing. Okay, we'll do more at Sim on Wednesday.